Great. Yeah, so hi, welcome everyone to Learn and Share. PSC, we like to put these on here and there, just kind of shine a spotlight on things in the space that we think are interesting and people can learn from. I'm Sinu, I'm here at PSC. Most of my focus goes towards developing the TLS Notary project. Today we have a great guest presenter, Xiao Wang. Xiao's an associate professor at Northwestern University. He's the chief cryptographer at Primus Labs and is also an author of the Quicksilver protocol, which I believe right now is currently considered the state of the art of the so-called vector VOLE-based Zero Knowledge protocols that he'll be presenting about today. I've been interested in these protocols for some time now. They really stand out in terms of like both prover performance, low memory overhead, and they're actually quite simple as well. Relatively simple, and albeit there are trade-offs when it compares to other proving systems. It's not better across the board, but it has some really interesting characteristics for client-side proving. TLS Notary project, we recently incorporated this into our protocol to great benefit, and I just think that other people should be aware of it and to take it into consideration as an option when they're developing like client-side apps. And yeah, that's enough for me. I'm going to pass it over to Xiao. He's gonna share a screen and we can get going on a presentation here.
Yeah, thanks Sinu for the introduction. I'm going to share a screen. I'm going to share the entire screen right now. Allow. I think you should be able to see my screen. So today, I'm going to talk about some high-level overview of VOLE-based zero knowledge proofs. I'm not going to cover all the technical details, but I hope to at least give people a feeling and some kind of intuition why this is lightweighted and what kind of applications it might be suitable. So we also zero knowledge proof is so if we view it as a so-called ideal functionality, so we could view it as a so-called ideal functionality. You can think about it as a I think so. I'm not able to see the chat. So if somebody send something in the chat, then I need to.
I'll chime in and I'll let you know.
Okay. Yeah. So you can view it as a trusted party who take the witness from the prover and then check the predicate and whether the predicate is satisfied.
I think your screen share went away.
Okay. I think maybe because I exit. Let me show it again. Entire screen. It should be good now.
Great.
Yep, and the trusted party can essentially verify the predicate and send the result of the verification to the verifier. And I mean, there are different levels of definitions of zero knowledge proofs. For example, what does it mean by the soundness? What does it mean by zero knowledge and things like that? But that's not really the focus of this talk. So I mean, I'm just going to use this to briefly talk about mention the properties. So there are many different kind of approaches for zero knowledge proofs, including, for example, the ZK snarks, like the IOP-based protocols, the GKR, which is kind of very closely related to IOP-based protocols, and some less known protocols like MPC in the head and zero knowledge gobble circuit like protocols. So I made a so one way to kind of classify all the types of zero knowledge proofs is that we can try to see different kind of dimensions. Okay, so one dimension is interactive versus non-interactive. So we have proven and verified that the interactive protocols would require more than just one message from the prover to the verifier. There could be multiple messages going between them. And the non-interactive, well, it means that prover just need to send one message to the verifier. Something related to interactive and non-interactive would be designated verifier or not. So designated verifier means that the message can only be verified, or the protocol can only work with a particular verifier. So majority of the non-interactive zero knowledge proofs are not designated verifier, which means that any verifier can verify. But there are some non-interactive zero knowledge proofs where the verifier has to set up a very specific CRS, so it is designated verifier. For interactive, almost all of them are designated verifier, and this is actually one of the important features Oh, I mean, so it's you can view it as a bug or feature, depends on the application. I will talk a little bit more about that. And in terms of the succinctness, there are protocols that are more or less on the high end of succinctness, which is either where the proof size is either independent of the statement or it's like a polylogarithmic to the statement. There are some somewhat succinct protocols where it is more on the, like, for example, square root of the the statement. There is like I guess the typical example would be Liharo for somewhat succinct. There are many. I mean, I would say like majority of the ones that people know are succinct, and there are also protocols that are not succinct at all. Like for example, the protocols I'm going to talk about today, and some other variants for MPC in the head and zero knowledge garbage circuit. And then in terms of the computational efficiency, I mean, like we can view it as 3 layers. Okay, the first layer is that for every gate or every statement or every constraint, we need a constant number of public key operations. Okay, so that means that we need a linear number of public key operations. So this would cover majority of the, for example, ZK SNARK protocols. And here, public key operations could be, for example, exponentiation in groups, or it could be some lattice-based operations. Okay, so something maybe better would be like some number theoretical transformation on the whole circuit. Then in this case, the exact complexity would be, for example, like n log n for n number of constraints. And then now it's really a matter of comparing like log n ordinary operation versus one public operation, which is more efficient, which is less efficient. And also, I mean of course, the best in some sense one could hope for is that we just need a constant number of symmetric key operations for each gate to prove a circuit. So this would be pretty much as close as what you would get, because in modern CPU, a symmetric key operation is not too slower than like ordinary operations. So this would just be a constant fraction slower than ordinary operations when proving something. And there are for example, trusted setups, like whether there is any trusted setup, whether the trusted setup is universal, or whether you need a different setup for different programs. These are not related to our talk, so I will not talk too much about this. And finally, something that has not been studied that much would be the memory requirement. So typically there are 2 types of memory complexity for the existing protocols. So one side would be memory that is linear to the size of the statement or the size of the circuit that has to be that needs to be proven. And the other one would be linear to the memory needed to evaluate the circuit, which could be much less than the circuit itself. So this is a little bit tricky. So let me try to explain it a little bit more. Okay. So let's say if we have a circuit and the circuit say just let's say the circuit verifies a iterated application of some hash function. In that case, let's say if the iteration has let's say if there are 100 iterations, then the circuit size is 100 times the unit step. However, in order to verify this, in order to run this circuit, we do not need to keep the whole circuit, because after the one iteration, we don't need to as a plaintext evaluation of the circuit, we can just we can forget part of the previous iterations. This is like when, for example, when we write a for loop, if some of the variables are local variables, when they are actually when we finish the iteration, these local variables will automatically be recycled. So verifying the circuit could require much less amount of memory than the circuit size itself. And that gap can be very, very big for real protocols. So I ordered them in this case because the top ones are what actually people has paid a lot of attention, while this where the lower ones are the ones where people actually hasn't paid that much attention yet. I mean, in the past few years, this has been more and more people realize that this is more and more important. But overall, memory requirement is something that people does not really pay that much attention before.
Do you have any thoughts on why that attention has been mostly focused on those other properties? Is that, well, I guess from my view, that might be an artifact of just, I guess, the blockchain space. And for example, having a smart contract verifier of a proof obviously needs to be non-interactive. And also there are bandwidth considerations as well. So it needs to be succinct, and there's just a high pressure there. Is that kind of like a fair thing to point to, or do you see it differently?
I think maybe this is a little bit orthogonal, because there are also snarks that can have a small memory requirement, or like smaller than the circuit size. So there exists the snarks where the memory requirement is not as big as the typical snarks. But this these protocols, the computational complexity is higher, but the memory requirement is lower. I think people didn't take memory complexity that much because, I mean, maybe in the past maybe 20 to 10 years ago, snarks are too inefficient, such that the memory is not the bottleneck. It's really the computation that becomes the bottleneck. And once people, for example, realize that they can actually prove, the prover can prove, say, 1 billion gate in reasonable time, then they realize that okay, they can prove a much larger statement that actually captures real world needs. But then they realize that okay, so they are out of memory, and then so they have to, the protocol has to be sufficiently efficient to hit the memory bottleneck, and then people will start considering a memory requirement. So before that, people memory is not even a bottleneck. They can always open a, say, 128 gigabyte machine to do the proof. But now, if the demand on snark is higher and higher, and the statement becomes larger and larger, cannot make it arbitrary. You cannot slightly economical to just add memories, and finding a protocol that is memory efficient may be a better way to do that.
Right, that makes sense. Yeah. Especially with the pressure to kind of move this stuff more towards being on client side, running on mobile devices, running on personal computers and such. Thank you.
Right. Yeah. I mean, another line, another recent line is all these outsourcing snarks, and some of them also support kind of parallelization, meaning in the sense that let's say if a prover has a circuit to prove, they can distribute the task into n number of workers, such that the memory cost is also distributed among n workers, to kind of there are scale up and scale out two approach. This is a scale out approach for reducing the memory requirement per worker. But I mean, in the end, if there is a way to use algorithm and protocols to reduce the memory requirement, that would be even better, because not everybody can afford a cloud. Yep. Okay. So I mean, I made this graph. I mean, figure to show the high level classification of what I see as I mean, some kind of a high level partitioning of existing works. So there are many succinct and non-interactive, but there are also linear-sized non-interactive protocols. Some based on MPC in the head, some based on VOLE in the head, which combines VOLE-based zero knowledge, which is interactive, along with some other techniques, and also some cut and choose Gabor circuit. Actually, there exists the protocols like this, which is also non-interactive, but the communication is a lot higher. Okay, and on the interactive side, so before the line of VOLE, the only one that is practical is the Gabor circuit-based zero knowledge proofs that requires, I mean, pretty much 128 bit per second of communication. So that's fairly high. Okay, so in the VOLE-based zero knowledge, it's not just myself's work. There's there are multiple teams in academia working on VOLE-based zero knowledge, and in the past 5 years, I mean, it's it's everybody's effort, and we are able to make this VOLE-based zero knowledge very lightweighted. So concretely, let's say if you want to prove a circuit of size n, then the proof size would be n bit, and the majority of the communication is from the prover to the verifier. However, there are some number of interactions between the two parties. So the proof is interactive protocols that require prover and verifier to talk for some number of small number of rounds. I think it's probably less than 10 or maybe less than 5. And the majority of the communication comes from the prover to the verifier. And the communication is about 1 bit per gate. Yep. And like the computation is very cheap. We only need constant number of symmetric key operations. So it is way faster than any other zero knowledge proof protocols. And I hope that in the next 40 or 50 minutes, I will convince everybody why this is the case. Okay. So essentially, so Snarks is really good for this kind of asynchronous setting where we have one prover, and the prover wants to convince the prover the knowledge of some witness to a bunch of verifiers, and that when prover generates the proof, the prover doesn't know the identity of all these verifiers. That's where Snarks actually shine, because the prover is kind of asynchronous in the sense that when prover generates the prover doesn't need to know the identity of the verifier. So there are also other synchronous settings. So for example, the most synchronous setting would be when prover wants to prove something, prover already can talk to the verifier. So the two parties are online at the same time. So in that case, the prover can just prove to the verifier directly. And in this case, an interactive zero knowledge proof would make more sense. So obviously, well, any application, all the applications on the synchronous setting can also use a asynchronous solution. For example, the Snarks. They also work on the left-hand side because the left-hand side is, you can view it as a more restrictive setting. But it also means that there are opportunities to optimize and improve the efficiency on the left-hand side. So if we don't need a synchronous like a notion, then maybe we can do a lot more better, by actually utilizing the fact that two parties are online. Okay, so that's really what we want to do. So the protocol I'm going to talk about is interactive, and it's often linear. I mean, if it could be sublinear to the statement size if somebody actually try to optimize the circuit carefully. So there are actually ways to optimize. The communication is at most 1 field per gate, and for Boolean gate, 1 field will be just 1 bit. So the efficiency is the constant number of AES, so a constant number of hardware accelerated AES operations, and a constant number of hardware accelerated finite field operations per gate. And I mean, so both of them are hardware accelerated because this GAWA counter mode GCM, which is part of the HTTP standard, which also encrypt the, I think 99.9% of internet traffic actually requires using AES and extension field operations. So pretty much every computer right nowadays has a module to accelerate operations for AES and finite field operations of this particular field. And so the protocol actually only requires a constant number of both of these operations when the constant is actually small. Okay, and the memory.
We have a raised hand. I believe it was Alex.
Go ahead.
Yeah, I wanted to ask, is being field agnostic a difficult thing to achieve in VOLE? Because I know it's a big thing to achieve in the traditional Snark world, or is it pretty simple to achieve in the MPC in the head setting?
Yeah, I mean, so for our protocol, it pretty much support any field. There are also extensions to support integer rings, operations modular 2 to the 6, for example, modular 2 to the 32 natively. So it's actually a lot more flexible than Snarks and other stuff.
Cool.
Yeah, and so what I talked about, I mean, I think from this, after this point, I think a majority of the slides are actually already field agnostic. You can actually interpret it in any field that you want. I mean, the protocol also works even for small field Boolean or Z3, Z5. It also works on this kind of even smaller field. It really depends on the application, what you want.
So that's also in combination with the fact that you don't have to hold a field element for, I guess, every gate in the circuit, right? You can drop essentially as values are no longer needed. So that really provides a very low memory overhead. It's quite cool.
Yeah. So to be technically correct, if the field is small, they need to hold a MAC of the value, and the MAC would still be 128 bit, around 100, like a computational security parameter bit. So even if the field is small, the MAC is still slightly larger than that.
Ah, I see.
Yeah, but
Yes.
So for majority of the nature programs, like we write like many majority of the wires are really just local variables, and they can be forgot pretty quickly, because so that's essentially the biggest advantage of the protocol. So the size of the MAC is not turns out to be not the bottleneck in memory. Yep. And we don't need any trusted setup. That any two parties can just directly, as long as they have PKI, they know each other, and then they can just directly run the protocol, and it is UC secure. So it's as secure as one could hope for. Okay. Yeah, and this is kind of the best one could think of, because even if we wanted to actually evaluate the circuit in the plain text, we still need one instruction for that gate. Okay, and the throughput of AES is about one or two in cycles per AES. So so these are pretty much a constant factor slower than what you need to evaluate the circuit. Okay, so there are two main components. The first component is to quickly authenticate the protocol, and the other component is to quickly check the authentication without revealing the information. And then there are actually all different kind of operations that we can support. So in order to support this kind of quick authentication, so we have one work published in 2020, which is called Ferret, that follows a long line of work on pseudo-random correlation generators. I think I have a few slides to give a high-level overview of what it does, and maybe I can talk more maybe next time when we have a chance exactly how it works. And I will talk about I will focus more on how to actually check this gate efficiently, and why checking this gate only requires field operations and AES rather than any heavy operations. And so our first protocol for the checking was published in maybe also 2020 or 2021, I can't remember. But so we call it the Wolverine, and we have we have follow-up works, and the other groups also have more and more works building on top of this paradigm to get it more and more efficient and more capable. Okay, so this is the first important slide. So if you can't remember, can't remember anything that I talked about so far, then this is actually the one slide that is very important. Okay, so we have a prover and a verifier. So we want the prover and the verifier to establish some kind of information theoretic max. So the information theoretic max can be viewed. I mean, it's a tuple of two values on each side. So on the prover side, the prover wants to supply a value x and get a value m sub x. So this value m is related to x. That's why we call it m sub x. And on the verifier side, the verifier has a delta, which the verifier will use across the whole protocol. So this delta is fixed, and the verifier will protocol will give the verifier a value k. So these are just some values, and they satisfy this kind of relationship. Okay, so this is essentially a MAC. So this MAC equals to the key that is sent to the verifier plus the bit that the prover get times delta. So so what's happening? So what is this? So essentially, we can think about it. So delta is something that verifier pick uniformly, and it doesn't has anything to do with x. This kx is also uniform from the verifier's view, and because kx is uniform, so it means that kx doesn't does not reveal anything about x. So this information theoretic MAC is so-called zero knowledge or hiding to the verifier. And then from the prover side, prover has a value mx equals to essentially this value padded with x times delta. So what this means? So now so this is a authentication of the value in the sense that now if the prover wants to convince, like let's say later, if the prover wants to convince the verifier that at this point the value is x, then the prover can send x and mx to the verifier, and then the verifier can verify whether this equation is true or not. However, if the prover wants to cheat and send a different x prime, then the prover has to actually figure out a value mx prime that also satisfies this equation, because this is what the verifier is going to satisfy. Okay, if this is doable, then like we know that this is true and this is also true. If the prover can figure out both of these two equations, then the prover can essentially solve these two linear equation and figure out what is delta. But delta is never sent to the prover, so the prover would require it's not computational feasible to compute the delta. That means that it's not computational feasible for prover to figure out to open the value x to a different value x prime and let the verifier accept the value. So this can be viewed. So this is essentially some way to authenticate a value to the verifier without revealing the value. Another way to think about it is that this is pretty much a commitment of the value x. So this can be viewed as an interactive commitment from the prover to the verifier, such that the verifier holds the commitment, which is this value, and the prover has the opening of this value, which is this value. If the prover wants to open, the prover can send this value. This is hiding and also binding because of what I just said.
Is this where the OLE comes from, in vector OLE?
Yeah, so this is so because this delta, so this is a so this relationship is OLE and OLE. Okay, so if this delta is fixed across many correlations, then this is a vector OLE in the sense that there will be many vectors of m, many vectors of k, and many vectors of x. But the delta is the same delta. So this is really the vector OLE. So vector OLE is just defined as this ITMAC computation where delta is fixed. Yep. And so this thing is actually very nice because this has many nice properties. Okay. So the first property is that, so I'm going to use this bracket x notation to denote the configuration that the prover has mx and x and the verifier has a kx. And if the two parties hold a authentication of x and authentication of different x prime, then they can locally compute the authentication of the summation of them by just locally computing all the values as the summation of just sum up their own values respectively. Then that becomes the so-called the authentication of the summation of the values. And it is also you can also add a constant to the authentication by the verifier updating the value. And two parties can also you can also multiply a constant to it. Two parties can just multiply the constant to their own values, and the relationship still hold. This is so all of them hold because the constraint itself is a linear relationship. So all the linear operations on top of this linear relationship is still good. Okay, so this is nice, and this is actually very efficient to generate. So for Boolean, where we need VOLE on top of extension field, this pretty much takes 14 nanoseconds per entry. And for a larger field, let's say if for this Mersenne prime field, then it's going to take 85 nanoseconds per entry because some of the operations are slightly more inefficient. But these are on the nanosecond level in terms of the efficiency. We actually spent a lot of engineering effort when we had the paper in order to minimize the cost, and because this is really on a nanosecond level, even one more memory copy is going to kind of increase the cost by a lot. So actually, we took it was quite a pain to actually optimize as much as possible, in this project. But the protocol, our implementation is open source, so if anybody who wants to use it doesn't need to actually optimize it anymore. So this is the cost for for the semi-honest case and the malicious case, and for the rest of this talk we need actually the malicious case. So this is something that we are more interested in. So so in order to generate one such correlation, the communication is a 0.044 bit per correlation, and the cost is 17. And when the bandwidth is small, and it's about 14 when the bandwidth is larger. Yep. So this is so I mean, like, I hope everybody is convinced that this, like, we can generate this kind of stuff very, very efficiently. Okay. And like they are like I think I may talk about, I think I talk about the construction of this kind of protocol. Like I put the slides like at the end, so like if we have time, I can briefly talk about how the high level idea, what are the operations needed to generate them. Yeah, but
just to linger here for another moment. So addition and multiplication and with constants are free operations, as well as just addition is homomorphic itself. Yep. And it takes about, back to your slide there, 17 nanoseconds to prove a multiplication.
Oh, so this 17 is to generate a correlation like this. Set up this kind of correlation requires 17 nanoseconds.
Oh, I see. So this figure doesn't include, I guess, like total proving time for a multiplication.
Yeah, not yet. I think I have a slide after talking about the protocol to give numbers, and then the number is like include this cost and some other costs needed for the zero knowledge proofs.
Great, thank you.
Yep. Yep. So like so as I said, like so we want like we want the like small memory. So we want the memory to be as small as possible. So this means that we want to follow so-called the gate-by-gate paradigm. So what does it mean by gate-by-gate paradigm? So essentially, so essentially, let's say if we have a circuit, we want to, like, once we prove a portion of the circuit, if the internal wires of the circuit are no longer used anymore, then we want them to be like, we want to kind of deallocate the materials that we stored for them. So let's say so the first step in this kind of protocol is to actually authenticate the input. Let's say prover has a witness which contains, say, an element, and we want to first authenticate this element to the verifier so that they hold the authentication of the witness. Okay, so the two parties using the previous method can generate a authentication on a random value, and then the prover can just send the difference of the witness and the random value to the verifier. And then this value is a public value between prover and verifier. So they can just add this value to the authentication. And by the homomorphism, the summation of these two values will give us the authentication of the witness. So in order to authenticate the witness, we just need to send exactly the amount of information linear, I mean, exactly the same as the size of the witness. So now two parties hold the authentication of the witness. So now let's say if we have a circuit, let's say if I have maybe I can draw a circuit. I can just draw a circuit quickly here. Okay. So let's say if I have a circuit here, I'm going to draw one more gate here. Okay. Okay. So what we wanted to do is that we want to first authenticate all these values. So two parties hold authentication of these values. Okay. And then we wanted to run a protocol to convert these authentications to the authentication of the output wires. And once we have the authentication of the output wires, we do not need to hold the authentication of the input wires of these two gates anymore, because these two wires are no longer needed at any part of the circuit. So we can kind of deallocate the authentication for the input wires. So after we prove the first gate, we only have like 3 authentication. Let me see how I can change the color. Okay, maybe I can change. So after I prove this gate, I only need to hold this wire, and this wire. I only need to hold this 3 wire, the authentication of this 3 wire. And then I can, after I'm done with this, I can prove this gate. And after I prove this gate, I can hold the authentication of this wire. And the authentication of these 2 wires are no longer needed. And then after I prove the first 2 gates, I just need to hold the authentication of these 2 wires. So although the circuit is large, I do not need to hold the authentication of all the wires at any point. I'm going to kind of throw away the authentication after I finish the proving of the gate. I mean, as long as this wire is not used elsewhere. And then I can, for example, I can prove this gate, and then I just need to hold the authentication of this one. So I can just progress I can just for example use a topological ordering and dynamically forget about some of the authentications to reduce the memory. And this can all be done if the front end is smart enough. I mean, pretty much any program language will know which variable is local variable and which variable is not. So it's fairly it aligns well with existing understanding from the program language side. Okay, so with this kind of paradigm, the important thing is this unit box. Okay, so given the authentication of the input, how to obtain the authentication of the output. So that's the most important thing. Okay, and for addition gate, it's easy because it's additively homomorphic. So if we have the authentication of the input wires, computing the authentication of the output wires is free. It's just local computation, just addition. So if this is a addition gate, or if this is a XOR gate, then this kind of propagation of authentication is easy. So it's really just the question when it is a multiplication. So when it is a multiplication, then it will become more difficult. So here, this is the case of addition. Is just people can just do the homomorphic addition locally. So when this is a multiplication, so the prover and the verifier hold the authentication of the input values, which we denote them as alpha and beta, omega alpha and omega beta. So these two values are authenticated. Okay, authenticated by the max and keys. Okay, I have here. So these two values are authenticated, and the parties have max and keys. So now we can first assume that the prover is going to do the operation. I mean, it's going to be honest. In that case, the prover can actually send the multiplication of the out. So essentially, this is what the output is supposed to be, and then the difference of a uniform authentication, and then the parties can kind of obtain the authentication of the desired output by actually doing a homomorphic addition of this public D value. So why this is value? Because so D equals to this value, and we add this to SI. So SI and SI will cancel out. So this will give us omega alpha times omega beta, which is the desired output. Okay. So if prover is so this means that for every multiplication gate or AND gate, we are going to send one value that is exactly the size of the field. So if this is a Boolean gate, we send one bit. If this is an arithmetic gate, we send one field. Okay, but this is assuming that the prover is honest. So if prover is honest, then everything is good. But I mean, of course, the prover may not be honest, and that's the whole point of soundness in zero knowledge proofs. Okay, so in some sense, the job is that we have so for a gate we have authentications of two values and also authentication of the output, and we want to check that the authenticated value is actually a correct multiplication. So that's the whole job. Okay, so essentially almost all of the VOLE-based zero knowledge proof are the same up to this point. Okay, so every VOLE-based zero knowledge proof, I need to kind of first do something so that the parties get the authentication of the input and output, assuming that the prover is honest. Okay, so now we have because we have many gates, so we have many tuples of this kind of authentication triples. So now the rest of the job is really to check whether all these authentications are correct, whether these actually form a correct multiplication relationship. That's really the whole point, and that's how a different works, and try to do it more efficiently. Okay, so in our original work, which is Wolverine, we actually adopted a very classical idea by NNOB. This is a paper, I think, maybe around 20 years ago. And the context was, so this paper I think it was published in Crypto. So it's Crypto NNOB. I can't remember the year, but it's definitely more than 20 years ago. So this paper was about making a classical MPC protocol maliciously secure. And in that paper, they talk about a particular way of checking this kind of triples, which is so-called cut and bucketing. So essentially, like in the Wolverine paper, we essentially observed that actually that kind of idea can be used here with a slightly better efficiency. Okay, but I'm not going to talk about the details of this because this is no longer the state of the art, and this is fairly complicated to explain. So I just want to give people some kind of a context or kind of a history of how the ideas like evolves over the years. So this is kind of more or less like borrowing from the previous like existing work and try to do it in the black box way. Okay, and there is another work that also try to use like the black box feature of the commitment, so it will work for any additive commitment. So that's the mac and cheese paper, which also follows a similar line, but they have a different way to do this kind of checking. But both this Wolverine and mac and cheese try to do this checking using so-called black box way. So this is less efficient but more general. However, like so in the Quicksilver version, we are going to do it in the this is let me try to put it somewhere else. Can you still see my screen?
Yeah, looks good.
Okay. I moved the Google Meet like a floating bar a little bit, so I want to make sure it still works. Yeah. So so this Quicksilver actually doesn't use this kind of authentication as a black box way. It actually utilizes the fact that these authentications are linear. So this is where the improvement comes from. Okay. So essentially, like remember that so we have all these three tuples. All of them are authentications, and we want to check whether the multiplication of these two values equals to this value. So that's what we want to check. Okay, so we want to check this value, and we know that this is true. Okay, so we know that this is true already. Okay, and we want to check whether this is true. Okay, so in order to check that whether this is true, we are going to plug in the fact that the things that we know back to this kind of relationship. Okay, so we have omega gamma. So omega gamma can be replaced by some of the like values here, because omega gamma we can rewrite this relationship as like as omega gamma. So that's essentially what we are doing over here. Okay, so omega alpha equals to let me try to see. So so this value is like, so all the max are known to the prover, and all the keys are known to the verifier. So so essentially we can compute all of them locally. Okay, so this is some value that the prover can compute, and this is something that also the prover can compute, because the prover knows the original value and the MAC. Okay, and this is something that the verifier can compute, because the verifier has delta and the verifier has all the keys. Okay. And delta is so essentially so we want to have this term, and this term this should be gamma. Okay, this should be gamma. So and this should be alpha. Why I have all of them as beta? So this should be alpha and this should be beta. Okay, so this term is supposed to be 0. Okay, so checking whether this equation hold. Checking whether this hold essentially means that whether we want to check whether this is a 0 or not. Okay, so let me maybe repeat a little bit and try to explain again exactly what's happening. Okay, so this is the kind of the key of the whole protocol. So we need to do all the sending, but this is really this is the most complicated part of the math, which is just a bunch of linear relationships. Okay, so prover the verifier has all these values. Okay, remember that verifier has the key. So verifier has the key. So verifier has all the keys for both of the input and the output. So verifier has key alpha, key beta, and the key output. Okay. So when we have all these values, we can write key alpha as m alpha plus omega alpha times delta. Okay, this is by definition. Okay, so key alpha equals to m alpha plus omega alpha times delta, and key beta can also be written in the same way. So that's going to be m beta plus omega beta times delta. Okay, and then minus m gamma plus omega gamma times delta, and then times delta again. Okay, so this equation equals to this equation. So this equation is something that the verifier can compute locally, and that equals to this equation. Why? Because we know this is how the relationships are set up. Okay, so now we have so there are 4 terms over here and 2 terms over here, because we have 2 terms here, 2 terms here, and the multiplication can expand to 4 terms, and we have 2 terms here. Okay, so if we rearrange all these terms, this will give us this value. Okay, so the left hand side equals to the right-hand side. And the right-hand side is the rearrangement of this term. For example, m alpha and m beta is just multiplication of this value and this value. And others are similar. Okay, so this is a rearrangement. We have 1, 2, 3, 4, 5, 6 terms. So exactly this 6 terms. Okay. So we know that left-hand side equals to the right-hand side. And if our job was to check whether this relationship is correct or not. If this relationship is correct, then this equals to 0. Okay, because right? So this term will be 0. And if this is 0, then this equation is really a linear relationship with respect to delta. Okay, so this is the key. Okay, so the two parties hold some value, and they can do some kind of local computation. Okay, after they do some local computation, they have 4 values. So the verifier, I'm going to use a different color just to distinguish from what I have before. That's this value, and the verifier has this value. The prover has this value, and the prover has this value. Okay, if the relationship is correct, then this term is going to be 0. Then the two parties hold some value that becomes a linear relationship. Because because this is delta, so this is like this again looks like IT max. So this is a linear relationship. Okay, if the multiplication is incorrect, then there is a quadratic term over here. Okay, so the job of checking whether a gate is correctly computed becomes a job of checking whether these 4 values satisfy this kind of a linear relationship. This is a line essentially. So this is a linear relationship. Okay, and in order to check whether this is a linear relationship, the easiest way is to first we generate a linear relationship, and then use the linear relationship to mask this relationship that is supposed to be linear, and then we check whether the difference is still a linear relationship. So that's essentially a way that we can do. So this is how I wrote it here. So if I have a linear relationship, and if I have a 2 linear relationship, then their difference is still a linear relationship. But if I have a linear relationship and a quadratic relationship, then their difference will no longer be a linear relationship. So essentially, that is kind of the intuition of how we can check a gate by using the fact that it is a linear relationship. Okay, but this is not good yet, because we still, for every gate, we need to send 2 values. That's not good. We don't want to send anything more, because this is going to be too much to send. This is going to improve, increase the performance. This is going to increase the communication a lot. Okay. But the nice thing is that if we recall that we have many gates in the circuit, means that we have many relationships that we want to check. So for every gate, we are going to check this kind of linear relationship for a different linear relationship for each gate. Okay. So now let's say if our circuit has say a million AND gate, then that would become a million linear relationships. Okay, so instead of checking each linear relationships individually, so essentially what we can do is to linearly combine all of the linear relationships and just check the linear combination of all of the linear relationships. Okay, so this uses the fact that if we have many linear relationships, then the random linear combination of them is still a linear relationship, and it is a linear relationship that the parties cannot arbitrarily change. Okay, so instead of checking, say, a million linear relationships individually, we are going to randomly combine these linear relationships. I guess using Snark word, it's kind of a fold of all the linear relationships into one linear relationship, and just check that one single linear relationship. And this turns out to be fine. So this means that in order to check any number of gates, the verifier just needs to send a seed to the prover. And then the prover just needs to send 2 field elements. So this is going to be 256 bits in total to the verifier. And that will and that's it for checking all of the gates in the circuit. So once the authentication are set up, the communication is really constant. There's not really anything that the parties need to send. And of course, this you can mirror it out. So it's really just one message from prover to verifier to check the relationship. Okay. So overall, the protocol works by first authenticating every wire, assuming that the prover is honest, and then the parties run a random linear combination of all the constraints on the wires, and get one linear relationship that they want to check. And then like they can check it like easily using using this kind of existing established linear relationship. Okay, so that's pretty much the high level idea of the protocol. Okay, so given that we have the protocol, so now we can actually look at the performance. Okay, so I think this is actually not up to, this is probably not the state of the art already. Maybe let me try to find the latest number on GitHub. I always keep my GitHub performance more or less up to date, but not my slides. So let me try to yeah, maybe I can I'm going to share screen again. So this is more or less what we can do right now. So for 50 megabit per second, if one thread, we can prove about 8.6 million gate per second. And if we have 4 threads, then we can prove about 19 million gate per second. So this is about, I mean, pretty much so at this point, engineering is more important than the protocol. There are a lot of engineering effort to make the protocol as small as possible. So how many nanoseconds is it? So it's 10 to the 9 over 19 over 10 to the 6. So it's about 50 nanoseconds per gate. This is end to end. It's every cost is included. So this is about 50 nanoseconds per gate. And I mean this and it's really just use the 50 megabit per second, because even if we go to local host, it doesn't improve the improvement. The cost is it's not getting more efficient. If we further improve the bandwidth, so it's so if as long as the bandwidth is higher, it's it's about 50, you can get pretty much the best the performance that we can get, which is about 19 million gates per second.
Do you recall how many gates are in the SHA-256 circuit? Just to kind of put into a metric that SNARK people might be more familiar with.
So SHA, I think it has 200K, about 200K for one compression. It's yeah. So you can do do the math. Yeah. I think it's 200K. I need to. I can't remember the.
That sounds about right to me. Yeah.
Okay. Yeah. I think it's between 100 and 200, or probably slightly more. It's on the order of hundreds of 100K. Yeah. So yeah, so it's a fairly efficient, and it's not only efficient, but the protocol is really lightweighted. We don't need any. Pretty much any CPU in the past 20 years has all the instructions that we need to push the performance. So we actually run the protocol on some kind of very small node on Amazon. So these are the smallest node that I can find on Amazon that are not this kind of a bursting node. For the burst node, the performance changes over the time. So these are the ones that are not bursty, and the smallest ones that are not bursty. So the cost of these are 5 cents per second per hour. So so we also run the protocol on this kind of instance. So I think I made this slide maybe 3 years ago. I don't know I think maybe the price of latte increased a little bit, but anyway, so for the price of one granny size the coffee latte from Starbucks, we will be able to prove this number of AND gate. So this is what? This is 3,000 billion AND gate. So you pretty much I don't know. I would say that whatever statement that you wanted to prove, you can prove with a cost with the cost of less than 1 latte. If you need a circuit, if you actually want to prove a circuit that is larger than 3,000 billion gates, I would really be interested to know what's the statement and try to see whether there are ways to actually optimize it even further. Otherwise, it's really efficient. And in terms of the gate cents per gate, gate percent is I don't know, 10 billion gate percent US cent. So by the way, cent is no longer issued officially. So maybe next time I should change it to something else. But maybe quarters and next time. So this is this. I don't know. This is the affordability is really as much as you could hope for from a cryptographic protocol. This is very affordable. Yep. And like we also did some not
Just
too
going to give a quick 5-minute warning. 5 minutes to the top of the hour. There's not a tight cutoff there, but just thought I'd let you know.
Yeah, thanks. Yeah. So we also did some apple to orange comparison because like we are like I mean like the one of the reviewer we really want to see comparison, so we added it for them. So I mean like so for example, so here we did a matrix multiplication of two like 1,000 dimension matrices. I mean there are many different ways to do like to prove like matrix multiplication in zero knowledge proof efficiently, but here we just like we try all of the protocol, assuming that we just like we don't know the structure of the matrix, so we just like use this as a way to increase the number of AND gate without number of multiplication gate without getting too much trouble. Okay, so for like state of the art like zero knowledge proofs at that time, it actually requires quite a lot of execution time, well, because it is like a big circuit, but the proof size is very small. This proof size is like 100 kilobyte. However, it actually needs about 100 gigabyte of memory in order to prove this like a 1 million gate circuit, or maybe I think this is 100,000 million gates circuit, because matrix multiplication is n cube. Okay. However, for for the VOLE based protocols, they really just need 1 gigabyte of memory. Okay. The communication for like the first gen VOLEs are still pretty high, but like once like we using like the state of the art protocols in VOLE, they actually get much better. So like for example, the communication is like much lower, and if we and if you use like the special ways to represent the circuit, then it get really like small, like for this example. Okay, so there are like for some circuit they can actually like get very small, and it really, so here I think the circuit size is 10 to the power 9 number of multiplication. Okay, so we really just need a very small memory size for computing even like this kind of circuit. Okay, yep. So I hope now it actually so everybody is like understand what I'm trying to say here. So like where is the cost of AES? So there are two parts where we need AES. One is generating the seed and expand the seed for random linear combination, and this is for like getting the values that are supposed to be in finite field. So if we have a different field, then like well, like the multiplication will be on the target that field, and the communication is 1, and which it's interactive. Okay, so there are like a non-interactive variant, and that would be VOLE in the head like a work that is published more recently. Okay, and I mean there are more optimizations that but I don't think I have time to cover like more insight like multiplication like optimizations for some specific stuff. So I probably will stop.
Great though, you've covered a lot of ground. We have a raised question here, Ali.
Sure.
Yeah, could you please elaborate on circuit versus polynomial on the previous slide?
Oh yeah. So can you still see my slide?
Yes.
So yes, so there is actually maybe let me just go to here. So there is actually a improvement. I mean, I wouldn't say improvement. There's a variant in Quicksilver that can prove arbitrary number of polynomials with cost sublinear to the number of gate. So let's say, so here I'm illustrating, I'm proving 3 polynomials. All these 3 polynomials are computed on top of 5 input wires, and obtains 3 output wires, 1 for each polynomial. And the highest degree of the polynomial is 5. Okay, so in this case, although there are many gates to compute these polynomials, the cost of like the communication cost of our protocol would be the sum of the input wires, output wires, and the highest degree of all the polynomials. So in this case, so if the computation can be represented as a bunch of polynomials where the degree is bounded, then there is actually a way to actually further reduce the communication and further increase the performance. So this is what I mean by polynomial. So this is this extra optimization that is actually very useful. So this has found like many applications, especially in the VOLE in the head. So they actually use this optimization to optimize the computation of AES, because like in AES, it's really just a bunch of S box, substitution box, and the substitution box is really just a degree 8 polynomial. So they actually use this optimization a lot. So this is just a way to actually further reduce the computation. Yeah, so this is what I mean by polynomial over here. So circuit is the baseline protocol. Polynomial is the more optimized protocol.
Great. I hope that got your question there, Ali. All right, yeah, so we're at the top of the hour. We've covered a lot of ground. I feel like there's still so many things that I personally would like to ask and so many things to cover, but we've only got so much time here. So yeah, we'll definitely want to consider maybe splitting this out into multiple different things in the future here, pending interest. But yeah, thanks so much, Xiao, for your time today and for giving us a rundown on kind of a different class of zero knowledge protocols that people, at least in my circles, don't really look at all that much. And yeah, it's been awesome to have you.
Thank you. Yeah, like if anyone has any questions or want to try it out, like feel free to email me or actually also email Xiang, like because tell me know more about how to use them in like applications. But if you have any technical questions, also can feel free to email me.
Great. So email's a good way to contact you. Any other venues you want to put out there?
Yeah, maybe let me put my email.
Hopefully that will capture in the video recording, but if not, we'll put it on the YouTube description as well.
My email is also on my homepage, so it's not a private secret, so it should be fine.
Perfect. All right. Well, thanks so much for joining, everyone, and yeah, we'll catch you next time. Thank you, Xiao.